Good. So I'm Adeel Hassan, and I'm a machine learning engineer at Element 84, and I'm going to be talking about vector embeddings, in particular vector embeddings derived from geospatial imagery. And the overarching point I'm trying to make with this presentation is that these are kind of a big deal for the geospatial domain, and something we should all be excited about. And to do that, I'm going to be giving a quick tour of a bunch of capabilities that people are starting to build out. That includes us, Element 84, as well as others, uh, entirely with open source models, data, and tooling. And but I also want to emphasize that all of this is very new. So, so there are challenges that need to be overcome if you want to scale it to a truly scale these capabilities to a truly global level. So I'll be giving a tour of different capabilities, but I'm going to start off with a quick recap of what vector embeddings are. And so, as you might know, they're essentially a lower dimensional representation of high dimensional data. And this high dimensional data might be in the form of images or text or video, audio, or basically anything, literally. In the context of geospatial, these images might even be multispectral or hyperspectral. The idea is that you pass it through an embedding model, which we'll talk more about in a second, but just imagine a neural network that outputs a list of numbers, which is our vector embedding. And these embeddings, vector embeddings go by different names that you might have encountered elsewhere. They're also called encodings or feature representations or latent representations, or if you're feeling particularly fancy, thought vectors. Another thing to point out is that by low dimensional, I don't really mean low dimensional like 2 or 3 or even 10. These vectors are still hundreds or up to 1,000, or I should say thousands of dimensions. But compared to the original data, which might be like millions of dimensions, it's still a huge reduction. And by reduction, I don't just mean that this is a simple compression. It's kind of a more meaningful compression, if you will. Right, so the embedding model takes in these high dimensional data and outputs these vector embeddings, which can be thought of as points in an embedding space. So what's going on in that embedding space? So these list of numbers are, describe the coordinates of these points, their locations in the space. And the thing about this space is that the coordinates themselves, or the absolute locations of points, are not intrinsically meaningful. What's important is their relative position to all the other points in that space. So we can talk about the notion of similarity and dissimilarity in this space in terms of closeness in the space. So if 2 points are closer together in the space, that means that the data that they were derived from were similar to each other. And conversely, if they're far apart, that means the data that they were derived from were dissimilar. We should also, that was not planned. Okay, we should also remember, we can also think of these points as directions in this vector space. So you can think about doing things like addition and subtraction using these vectors. A classic example of this is from the field of NLP in the context of word embeddings, where if you subtract the vector of the word embedding of man from woman and do the same thing for king and queen, you see that it results in a very similar vector. So you can think of that direction as somehow encoding the concept of gender. And now a brief word about where these embedding models come from. So they're kind of a natural result of how neural network models work. So in a lot of architectures, the model naturally compresses the data as it passes work. And you can think of it as the model building up an understanding of the data until it finally outputs something, whatever it's being trained on, based on that understanding. So the dark green thing here is our vector embedding. So you can get it as a byproduct of supervised training. Or you can specifically train an embedding model using self-supervised learning, which might be contrastive or generative, as in an autoencoder. And in each case, you just keep the initial part of the network, the encoder, and throw out everything else, and you have your embedding model. So yeah, I think we're ready to jump into the demos. And first, we'll talk about some use cases that exploit the notion of similarity between vector embeddings. So the first of these is a demo from a company called Earth Genome, where they've embedded a large number of images from, I think, the state of Alabama. And what you're seeing here is a clustering of those points in that embedding space. Now, I should point out this is not the actual embedding space, which is hundreds of dimensions. This is rather a projection of that into 2D or 3D in this case. And what you can see in this demo is that similar images are clustered together. So as you see in the demo, all the images containing things like runways are clustered together like this, and as well as all the images containing solar panels, for example. And based on this distribution within that space, you can build out a simple classifier using nearest neighbors approaches. And this is exactly what this other demo that was built by the Clay Foundation does, where this is an interactive demo that you can check out at that link. And what happens there is that you can click on a sample chip somewhere on the map, and it that looks similar to that image that you selected, using essentially nearest neighbors. I should also point out that the embedding model used here is the Clay Foundation model, and in the previous example, the embedding model was something called SSL4EO. Both of these are open source and publicly available. Now moving on to slightly more use case. Quite the notion of dissimilarity between vector embeddings to do. And I also want to say /analysis because as you will see, this is kind of slightly, I would say it's slightly more informative than simple change detection. So here's an example of 3 vector embeddings of the same geographical location across 3 years. And if I ask you to pick out the here, it is a pretty easy task. And if you're able to do that, you've essentially done change detection without ever looking at the original images. And if you look at the images, this is what they look like. So the first one is from 2018, the second one is from 2021, and then 2022, where we see there is a flood. And so the embedding is completely different, and you can kind of automatically figure out whether it is different or not, and thereby do change detection. It's also interesting to look at the time series of these embeddings over time. So this is an animation that shows these vector embeddings from 2017 up to 2023. And the thing to notice here is that what is typical for this geographical area is not a constant, but changes throughout the year due to seasonal variation. This is an agricultural area, so we see crops are planted, then harvested at some point in the year. And we see a couple of occurrences of flooding in this animation where the embedding goes completely haywire. So it's a little hard to model 512 dimensional time series, but what we can do as a simplifying step is principal component analysis. And if you just take the first principal component, we see that it exactly encodes the seasonal variation. So if you plot it out as a series, this sinusoidal that describes the seasonal variation. And if you look at the blue dots, those are the cases of flooding, and we see that they clearly break the trend. A slightly more illuminating visualization is if we collapse this entire time series to overlay all the years on top of each other, so that we only have the months on the x-axis. And here we clearly see this U-shape describing the seasonal variation that is typical for this area. And the blue dots just show the cases where flooding occurred, and they stand out clearly. And if you wanted to automate it, we could fit a simple regression curve through it and see how much it deviates from that model. And you can imagine building an automated alert based on this deviation. I have another example here, which is from the Turkey earthquake from early 2023. And here we see that the PCA picks up the seasonal pattern. But if you look at the green dots, which is the post-earthquake embeddings, we see that they start to diverge. And which is kind of curious because they don't immediately diverge after the earthquake, but it did take some time. And if we actually look at the images, it seems that the damage from the earthquake did not register at the resolution of Sentinel-2. But what I'm assuming is like clearing out the rubble and reconstruction actually did. So that's what we see here. So from a third example, I'm going to talk about text-aligned image embeddings. And this is a really interesting idea where you essentially have two embedding models, one for images and one for text, that can embed data into the same embedding space. So an image of a house with a swimming pool and the text house with swimming pool will be mapped onto the very similar points in this embedding space. And that allows you to do really cool things like this demo here, where we can do natural language search based on the contents of the images. So even things like a single tree in an empty field, and it finds all the instances of those of images actually containing that meaning. And the way we do this is using something called language models. And we have a bunch of these that have specifically been fine-tuned on Geospatial, and are all open source. So one of them is SkyClip. There's also Remote Clip, RS Clip. And the reason they're all called Clip is they're based on this contrastive language image pre-training technique that was pioneered by OpenAI. But they did not actually release their models. So most of these are based on OpenClip, which is an open source version of that. And SkyClip is particularly cool because the text that it has been trained on was derived from OpenStreetMap tags. So yeah, content-based image search is something we can do with this. And just to give a brief overview of how we created this demo, we essentially found all the NAPE scenes that covered our area of interest, which in this case is the state of Massachusetts. And these are all the scenes and their footprints. And for each scene, we divided up the scene into small chips and embedded each chip individually. And that gives us a list of vector embeddings that we can compare the text embedding against. So for Massachusetts, using this particular tiling approach gives us around 560,000 embeddings. And so yeah, here's the demo again. And we've been calling this functionality Queryable Earth. And we have a blog post about it too, if you want to read that on our website. You can also do interesting things like interpolate between embeddings. So instead of having a single text query like dense forest or parking lot, you can query with both at the same time. And by taking a weighted sum of them. So as you can see in the images, these are the top search results of various combinations of these embeddings. So on the other end, you see a dense forest and a pure dense forest and a pure parking lot. And in the middle, you see a mixture of the two. And the amount of parking lot in the image seems to vary with the amount of the parking lot embedding in the mixture. Another very cool thing you can do with these vision language models is zero-shot classification. So instead of taking a text embedding and looking it up against image embeddings, you can do the opposite. Take an image embedding and compare it to pre-computed text embeddings. So for example, if you take this image and compare it against various classes like embeddings for classes like forest, harbor, stadium, parking lot, you can see that you essentially get a classification model for free. And you can extend this idea to land cover maps. So if you take all of the embeddings of all of the chips over Massachusetts and try to classify them into 3 classes like forest, forested area, urban area, and water body, we get a map like this. And this is essentially free without doing any special training. And you can also vary the classes yourself. The categories can be arbitrary. Now I want to go on a tour to talk about aggregating embeddings. I want to talk about H3 tiles. So I talked about how we tiled, chipped the scene into these chips of this arbitrary size. And the problem I always had with this is that this is arbitrary, and there's no reason why anyone else would want to use this particular chipping scheme. What they might want to do is use something more principled like H3 tiles, which are these hexagonal tiles that tessellate the world and are available at different resolutions. But to do that, you don't necessarily need to recompute or somehow pass hexagonal images through the embedding model. What you can do is take our existing embeddings and just do a spatial join. So if you take this particular hexagon, we can spatially join it with all the chips that it intersects with and do essentially a weighted sum of their embeddings to derive embeddings for each hexagonal tile in this grid. And with that, you can do pretty much the same thing. So this is a result of a text query, a large solar farm, but here instead of searching chips, we are searching for hexagons, and this is the result. You can also do land cover this way. So for example, for very low resolution hexagonal tiles, you spatially join all of them with the chip geometries and do zero-shot classification to get a land cover map like this. Or you could do it at different resolutions, so 8, 9, 10. So the path ahead is pretty clear. We want to just go ahead and embed everything that we can. But there are some practicalities and challenges that we would need to overcome before we can do that. And when I talk about scaling up, what that means in terms of numbers is scaling up to sizes of tens of millions of embeddings, because that's what it takes to, for example, to chip and embed the entire Sentinel-2 archive, both global and historical. So one of the things I've already mentioned is the chipping strategy. What should the chip sizes be? Should there be overlap? If you increase the overlap, that quadratically increases the number of chips. Should they be dynamic? Should we have more chips for more interesting areas and fewer larger chips for boring areas like water or deserts? Should they be standardized? Should everyone use the same chipping strategy, or can people go on and do their own thing, and then we do some kind of aggregation whenever we want to use them? Another concern is storage and sharing. For the demos I showed, we used GeoParquet to store the embeddings, and this is a screenshot of a geodata frame that shows these embeddings in a column, but this might not be the best way to store them. Maybe we want all the coordinates in different columns, or maybe we want to do something entirely different like GeoZar. Another important thing is floating point precision, which is a pretty significant, no pun intended, effect on the storage size. So if you imagine a 64-bit floating point integer, we can get rid of a lot of precision and store it something like 16 bits or 8 bits without too much loss of quality. And in terms of indexing and search, we found that using Postgres plus PG vector is good enough for a lot of use cases. You don't necessarily need specialized vector databases, but as we scale to tens of billions or even more, it might turn out to be that solution does not scale and that we need to move on to dedicated vector databases, of which there are several open source versions. And then maybe we also want a stack embedding extension to catalog all of these chip embeddings. And lastly, I want to mention Big Stack, which is this idea that Element 84 has started working towards, which is a newer, improved serverless implementation of stack search, which can scale to this scale of tens or hundreds of billions of items. And to close out, I want to I want to summarize my overarching point, which was that we have these geospatial images living in the cloud, and we want to access the meaning contained inside those pixels. But to do that, currently, we need to train specialized machine learning models that would interpret those pixels for us. But with embeddings, we can add other level of pre-processing to convert them into a form that we can directly manipulate using things like similarity searches, distance measurements, and arithmetic. And more concretely, some things that will become available soon, or in fact, people are already working on it, or you could contribute to yourself, is like global similarity search, global content-based image search, global land cover maps with arbitrary classes, heat map of change detection or anomalies. So imagine that regression curve I showed with the error color scales, and imagine that at a global level for each tile. And something I'm personally more excited about is for each location on Earth, we will soon have embeddings from multiple modalities, by which I mean embeddings from SAR imagery, embeddings from multispectral, from hyperspectral, and what have you. From multiple models as well. You don't always need to choose between models. You could just take embeddings from all of them. And using those, you could essentially do machine learning without ever accessing the actual large images. And that's it. Thank you. Before we take any questions, I want to point out that we have a couple of blogs that cover some of the topics I talked about that you should check out. And we also have a couple of talks coming up from Element 84. Yeah, I can take questions now. Go ahead.
So, Embed.